We're going to start with Mako P telling us about, well, several things, but probabilistic choreographies.
Because I would characterize this very much as application focused. But we're talking about AsInst, a language system model for asynchronous instructions so that we can do probabilistic performance modeling of choreographies. So we're starting here with the assumption that we have a choreography. In this case, Alice is going to take some input. She's going to send it to Bob and Bill. Bob's going to do some local computation on it. Maybe he's validating it, forwards that on to Bill. Bill computes the final output. We want to know, how long is this going to take? And of course, anytime you're asking how long something's going to take, that's going to depend on what it is you're actually doing. But it's also entirely possible that what it is you're doing is going to depend on how long earlier pieces of it take to run. So we have this sort of bidirectional feedback. Also, non-determinism is a very natural thing to end up with in concurrent systems, but it's not really sufficient modeling for what we're trying to do. We want to know what the likely runtime is, so we need a probability distribution over all those non-deterministic executions. I'll say up front, we're going to omit recursion. We're also going to omit functions. You could think of this as a compilation target or as a modeling framework. So whatever your source program is, hopefully it doesn't have unbounded recursion, because you're going to need to flatten it out into a list of instructions. OK, so we're building the AsInst instruction system. What do we need to support? We know we want to do local computations. We're not real picky about how those are written. So you're going to be doing some computation, and hopefully it is pure in the sense of not dependent on extraneous things that you can't model. But that's kind of all we care about with that. And we wanted to be able to do communication. So a value that's available at one party, at one location, one participant, will become available to somebody else later if it actually succeeds. It's not guaranteed to succeed. Or maybe it is. Maybe you're using TLS. Like, there are lots of different communication models you might be concerned with. And ideally, we don't really want to make this choice for you. Are you doing point-to-point? Are you going to do multicast somehow? Maybe you just have shared memory across your processes, and they can read values each other wrote. We'd like for you to be able to model any of these. So what AsInst provides you is a single instruction form, and you get to decide what it does. X is going to be bound to the result of S of Y's. As the user, you would have to specify what does S do. S is just a name. You're going to write the function body. So it needs a static cardinality and arity, and it needs a coherent type signature. And then that type signature is going to define what it actually does. So you'll have tuples. So if your input is int, what you're actually going to get is maybe a tuple, integer, and timestamp, but also maybe this diamond value, which is null, which is to say it never became available. And so you'll take your arguments, and what you'll produce is not an output or an output with a timestamp. It is a probability distribution, a joint probability distribution across values and timestamps, and also the special null value. So what we've defined so far is data flow programming. This original choreography I showed at the beginning has a really simple data flow diagram where the dependency graph is a nice directed acyclic graph. And guaranteeing that property doesn't actually require much in terms of a type system. You just make sure everything's declared in the right order and has coherent data types. And then when you add your probabilistic function bodies to that, what you get is literally a Bayesian net. It's higher dimensional, so it's not just on events, but on actual values, and actually the tuples of values, because the timestamps are baked into each node. But it is still a Bayesian net. And that's great, because Bayesian networks are a well-studied phenomenon. Or phenomenon's the wrong word. That's OK. I said we're not going to do recursion, but let's do conditionals so that we have something interesting going on. Modeling a conditional in a Bayes net is not fun to do. You have to add an edge from your guard to everything that happens inside all of your branches. Of course, we're interested in the timestamps of things, and we would like to accurately reflect the idea that the branches you don't take never happens. So if your guard evaluates to false or never, then that should force the output distribution of everything in the branch not taken to be the singleton distribution over null. And we have to consider what if the guard is null. And also kind of perpendicular to conditionals, but a lot of times we do things concurrently or in parallel. We don't always want to do everything in parallel. Sometimes one thing has to happen after another. So we want sequencing, the ability to say, don't do that until this other thing has finished. Our solution for that is our guard operation doesn't actually guard on values. It guards on the timestamp. So all of our instructions still only have one form. We say guarded on or gated on G. X is going to sample from S of Y's. And what that says is once or if G becomes available, then you can do whatever S says to get your X value. And if you don't want to gate on anything, that's fine. Just gate on 0, which we special case as always being available at timestamp 0. In order to do a traditional if-else clause, you need this translation. So we define two effects for you, gate true or gate false, that convert that Boolean into something that either becomes available when the thing it's looking at becomes available as true, or if it's false or it never becomes available, then it never becomes available. Gate false does the opposite. And so we can translate this very simple conditional into that completely flat list of instructions over there, where first you take your original scrutiny X, you make the gate the two gates from it, gated on those two, you bind your temporary variables Y in the true branch, Y in the false branch, and then you use first to combine those. First takes whichever one becomes available first, and because we wrote it this way, we know that only one of those, or at most one of those, will ever become available, so we don't have to worry that we're throwing out data there. And this gives us conditionals in a choreographic language. Specifically, we targeted a subset of Ozone to do translation and modeling of. It works out okay. So in a conditional, we have in Ozone, you have somebody, an owner of the branch guard, and they're going to deal with the conditionals exactly the way I just showed. Other parties, so I say here select and merge, and we haven't really talked exactly about how that works today yet. In a select and merge language, one party owns the conditional and is going to propagate knowledge of which branch they're in on a need-to-know basis out to other participants. So if you're coming into a conditional blind, well, we're going to assume that in your source choreography, everything was copacetic. The source choreography was well-formed, was projectable, and that means it was mergeable, which means that if you're coming into a choreography blind, it doesn't actually matter which branch you go down, just pick one. And by pick one, what I mean here is gate one of them on 0, or whatever you were gating on stuff on before, and gate the other one on never. And then when you get to a select, do bind that to a variable. Usually you wouldn't, but you're going to want to bind that to a variable. And the continuation from there will be gated on that selection variable that you received. This is not as tidy as I'm making it sound. There's annoying edge cases to make sure that the variables you want to use later in the choreography are actually named what you thought they were named and available when you thought they were available. We can put together some kind of pathological edge cases. And I think you can even write choreographies in Ozone that do not have a directed acyclic graph representation, which is interesting and surprising. Can we do the same thing for conclaves and multiply located values? It'd be nice if we could. Unfortunately, multiply located values, so far, we haven't been able to get to play nicely with failable communication. And in asynchronous instructions, it's not just that communication might fail. We care about when messages arrive. And there are very few, if any, situations where you would assume that all of the recipients of a multicast get it at the same time. So if this is what you want, that's future work. So we have the asynchronous instruction system. Hopefully I can answer more questions about it. But first questions are, okay, does it actually work? And how well does it work? And how interested in this should we actually be? So does it work? Yes, it does work. The Bayesian network interpretation that I've described is kind of analogous to the central semantics of a conventional choreographic programming language. We have a distributed analog in which instead of one big Bayesian network that takes place outside of time, we model every variable as a future promise, and those don't start running until their guard is available. And at each discrete time step, they look at the arguments that are available so far and probabilistically decide whether or not to resolve. And we prove that those two systems give you the same results, which is great because nobody wants to use the future-based semantics, and nobody has to use the future-based semantics. The caveat there being that you have to make sure that when you're defining the effects used in your program, they are realizable in the time step semantics. Even if you don't actually write out the realization, if you allow an unrealizable effect in your program, then you're going to get time travel, and I am assuming that you don't want that. But continuing on the idea that this works, we did implement some toy examples of it, so we could validate that we got reasonable results. I apologize for not customizing this graph for these slides, but the red lines at bottom show the concurrent execution made available under Ozone of an example choreography that can scale across the number of requests that are happening. The blue lines show that same choreography in the sequential semantics of Coral, and the green are the AsInst models of those two systems. So in the case of Ozone, it correctly identifies that it's going to be much faster. In the case of Coral, it nicely tracks the best case scenario, but there are some sources of latency that we failed to model, and so the actual likely evaluation is much worse than what AsInst predicted. So that gets into how well does this work? And the answer is, first of all, you have to have good models of your individual effects. The AsInst system doesn't help you write those. It doesn't help you determine that they actually model the things you're doing. But if they are good, AsInst will let you compose them and get a good model of the whole thing. The thing that AsInst actually gives you is a Bayesian network representation of the joint probability distribution of the entire program and every variable inside of it, which could be quite large. The good news is, or let's start with the bad news. The bad news is that Bayesian networks are not magic. The scaling with the number of variables is still expected to be exponentially difficult to compute on as the number of variables goes up. The good news is that that's a worst case, and Bayesian networks are nicely studied, and there are lots of special cases where you can do a lot better than that, and also a lot of practical cases where it looks bad, but when you actually run it, it turns out okay. Is this big, important work? Well, it's not that big an improvement on the status quo. A lot of the techniques I've described are not novel. So the Bayesian network I've described is a special case of a system described as a temporal node Bayesian network, where the nodes are annotated with timestamps. The distributed semantics, if you squint at it, is kind of doing the same thing as a dynamic Bayesian network, which has been studied for even longer than a temporal node Bayesian network. So I actually think the most interesting result here is that we're able to do this result on choreographies by just adapting off-the-shelf systems. That was the original promise of choreographic programming, was you can write your distributed system in a single program and do conventional static analysis on it and get results that apply to the real distributed system. So I think that's cool that this is just an incremental improvement. But we also didn't do this just to advance the state of the art. We actually wanted this for a bigger project. Specifically at University of Vermont, we're on the topspin team for a DARPA program. I promised you that PWN2 is pronounced doubly pwned. So we're studying weird networks, which is just the word for a communication medium, the use of which is difficult or impossible to detect by outside parties. And some of the early challenge problems are of the form, how long does it take to actually send something over one of these networks using all the cryptographic tools that it's built out of, which can involve retries, failable communication, a lot of random wait times between messages. And that is a pain in the butt to model, and that's what we built this for. So what does DARPA want this for? Well, stated purpose is to help people living under totalitarian regimes communicate amongst each other or with the outside world. Other obvious use cases would be to help American agents, I guess, in those same locations exfiltrate data, or to prevent, monitor against people in American data centers exfiltrating data. Last year when I presented at PLDI, it felt like kind of a non sequitur at the end of my presentation to remind the audience to fight fascism in our daily lives. And then on the plane ride back from Korea, America bombed Iran. So I, fingers crossed, have better ways of making the world a better place in my daily life than worrying about whether or not the work I've done here is going to have good or bad effects in the world. But we should be thinking about it. I forgot to start my timer. Oh. But here's the full preprint, which goes into all of the gory details. This is a practically oriented system that we intended to solve a problem and not necessarily to be mathematically elegant. So if you'd like to read it and ask me questions, or ask me questions without reading it, those are both great courses of action.
Your timing was perfect. We have about 5 minutes for questions.
I just have a clarifying question about
Yep.
the end of it. You said you were building this for a project. Was it then a smaller part of a bigger project, or did this give you the solution you wanted for some part of the weird network problem?
So this gives us, the specific thing that this gives the team is validation that their choreographic-ish system is actually going to model the way the real system behaves, which is like a lot of the time you would just say, well, we have this thing and here's our model and they look about right. And this lets us give a more formal proof, that the analysis is sound and will match what you observe in the wild.
I find this project really exciting as a guy working on the Coral programming language, and we just made an IDE plugin for Coral. One of the things we're looking at is interesting static analyses that we can run, and I think it would be really awesome to write a choreographic program and have an analysis that shows a little indicator at the very top of the choreography that says, well, the minimum time we expect is this, the average time we expect is this, and that's a hugely important in the context of, like, for example, cloud computing or something like that. So I'm wondering how feasible would that type of analysis be to do in a production programming language like Coral? And also you talked about performance. How long did it take to get that analysis?
So your second question first. I don't know. I worked on this with a team of people at Vermont. I should go up to the very beginning so we can see who they all are. It was Stephen and Ernest who did the physical implementation, and they'd be able to tell you how long it took. I know that when they start working on the actual challenge problems for doubly pwned, some of those run for hours or days. So building it into your IDE doesn't sound like the thing you're going to end up doing, is my guess. So you would need a mechanical translation from Coral into AsInst, and that would require a formal solution to those variable name problems that I mentioned when you're translating your conditionals. I think that can be done, but that is not something we have off the shelf at the moment. Right now it's by hand.
I'm thinking back to Kieran's talk from this morning. Could we do game theory with Bayes nets? How hard would it be to talk about that instead of performance?
I don't know. That said, is time the only thing we can talk about here? One way that I was thinking about this at different times was having two planes. So there's the data plane and the time plane, and they can talk to each other. But like you'll notice when I said these values have types, the type is just integer, and then the value is integer and timestamp. Could we add other metadata besides just time to it? What I found is that time behaves a special way, and everything else kind of just behaves like data. So yeah, you could put other metadata in there. It's going to behave more like data than like time, which is possibly a good thing.
Okay, we have time for maybe one more question while the next speaker gets set up. I have a question. You have the ability to have messages fail. What network assumptions are you actually relying on?
So you can write your own effects and decide what assumptions you want to make. We don't make any assumptions. If you want to have the assumption that one party can just read off of somebody else's hard drive magically, go ahead. If you want to assume that it's just UDP or something like that, then all you really need is a probabilistic model of how long or how likely it is for a message to get across. I guess the two load-bearing assumptions are don't do time travel, and more dubious, don't let effects affect each other. And like, that might not be realistic if you have limited bandwidth.
All right, let's thank Mako again.